So I had a question yesterday about current division, and said that Mr. Rabelais did it a different way than I did, and so I wanted to explain what the two different ways are and why they're equivalent, and maybe that'll help you understand and remember how they work. So if I have a current that comes and divides, so here's my current, and I'm going to do this by way of an example, and hopefully that'll help you understand a little bit. Let's say I have a current that is 3 amps, and I have a resistor here. One of them is 2 ohms, and one of them is 1 ohm. And we know that Ohm's law tells us that the voltage and the current are proportional, and the proportionality constant is the resistance. And so we know that given that there should be twice as much current, so 2 times the current should go through the 1 ohm resistor compared to what goes through the 2 ohm resistor. And so whatever current goes through the 2 ohm resistor right here, I'll call that I1, and I'll call this, that's confusing, I'll call this I2 and I'll call this I1. I should have twice as much current going through the 1 ohm resistor as the 2 ohm resistor. And so I know that I1 equals twice I2. I also know that I1 plus I2 has to equal 3 amps. And so I1 plus 2I1, did I get this backwards? I1 equals 2I2, yeah. This should be 2I2. I1 is 2I2. 2I2 plus I2 has to equal 3 amps, or 3I2 has to equal 3 amps. Or, now notice what's happening in this last step. I2, I'm dividing my current by the sum of what it end up being the sum of these resistances by 3. So I2 equaled 1 amp, and then I1 then has to equal 2 amps. And so what I needed to do is I needed to figure out how to divide this current up proportionally so that this resistor got this many times as much current, got as much times current as the other resistance, because the other resistor is what's slowing it down. And so the reason my current, the way I do current division and the way it's done in the beginning of the circuits book works is you take your I1 is going to equal your total current times, and then you're getting a proportion or a fraction of the total current based on the other resistor. So Z2, and then you divide that by the sum of the two impedances, because you need to get the part of the sum. So like up here, I knew that if I had 3 parts in all, 2 parts were going to go down this resistor and 1 part was going to go down this resistor. And sometimes it can be easy to see when you have it like that, and when it's not easy to see, you can just use this formula, because that's what this formula will do for you. It equals the other impedance over the sum of the impedances. Okay, but then you can also look at it another way. So let's say I have a current here, and this is I, and this current breaks up into 2 resistors, or 2 impedances. And I know what the total current is, and I find the equivalent impedance, and this becomes Z1, Z2 over Z1 plus Z2. So that's my equivalent impedance. Well, from that, I can get the voltage, because Ohm's law tells me V equals IZ, or V equals I times, in this case, Z1, Z2 over Z1 plus Z2. Okay, so now I know what the voltage is, and the voltage is the same whether I have the equivalent impedances or I just have one impedance. So I know that the voltage across these two impedances, so V equals Z1, Z2 over Z1 plus Z2. Well, now if I want to get the current through this Z1, if I want to get that current right there, I1, I know from Ohm's law that V equals IZ, and here I'm just looking at this this first impedance right here. The voltage is Z1, Z2 over Z1 plus Z2. That will equal I1 times Z1. So then what is I1? I1 is Z1, Z2 over Z1 plus Z2, which gets me divided by, did I forget my total current up here? I did. So that's I right there. And then and I'm solving, so I have my total current right here is I, and then dividing by Z1, and then my Z1s cancel, and I get I1 equals I times Z2 over Z1 plus Z2. But if I didn't solve for I1 right there, then so I just showed that they were equivalent, but now I could write this as I equals, or I1 equals the equivalent impedance. I'm going back to this equation. So I times Z equivalent equals I1 times Z1. And so I1 equals the total I times Z equivalent over Z1. So that's why it seemed like Mr. Rabelais' method and my method, and the method from circuits 1, seemed like they were backwards, but it's because this is Z equivalent. So I do I1 equals I times the other impedance, Z2 over Z1 plus Z2. This is not the equivalent impedance. This is the sum of the impedances. This is the equivalent impedance up there. So I just wanted to clarify, what was going on, why it seemed like there were two different ways of doing it, and that they were in fact identical. Okay, so are there any questions on that? And either way is fine. Either way will get you the right answer. Hold on just a second. I'll be right back. John? Yeah, I actually just glanced at the tablet. I was going to read it in a minute, so I didn't read what was on it. I didn't actually read the tablet. I just glanced at it and thought I'd read it in a minute. Is it still there?
Oh, no, but I sent you a text. It just says we're going on a dog walk, thank you, and it explains the money.
Okay, all right. All right, so at this point I am open for questions. The advantage of Mr. Rabelais' formula is it is the same, but you might have to compute Z equivalent differently. So if I wanted to get I1, that would still equal I times Z equivalent over Z1. Now what would Z equivalent be? Let's say I had three impedances Z1, Z2, Z3. Once you have more than two, you can't use our product over sum formula anymore. So the equivalent impedance, Z equivalent, is 1 over Z1 plus 1 over Z2 plus 1 over Z3. Now, what I tend to do, just because I'm so used to product over sum, is if I have more than more than two resistors or impedances, is I would say that I1 equals the total current times Z2 in parallel with Z3 over Z1 plus Z2 in parallel with Z3. So what I do essentially is I turn it into two impedances. So that's Z1, and then I find the equivalent of Z2 and Z3.
And that would solve the current going through Z1.
That would solve the current going through Z1.
So if you made Z1 and Z3 parallel, it would solve for Z2?
Yes. So if I wanted I2, it would be the total current times Z1 parallel Z3 over Z2 plus Z1 parallel Z3. So basically, what you're doing when when I do current division like this, however many impedances there are, I just turn it into two, and I make all of the others, I find their equivalent, and then that's what I have. So it would be I n equals the total times Z equivalent of everything else over Zn plus Z equivalent of everything else. Could I do the source transformation AC analysis problem on page 11? I can try, and that will probably take up the rest of the time that I have. So let me stop.